Hello and welcome back. So today our discussion is going to be on a new type of function called rational function. So the way it works is going to be a fraction with a polynomial numerator and a polynomial denominator. The first meaningful question we want to ask, what is the domain of f of x? So in a fraction, we're not allowed to divide by 0, which means x is not allowed to be 2. So we can say the domain is x cannot equal 2. Or we can write in interval notation negative infinity to 2 union 2 to positive infinity. Great. Now the next question we would like to ask is, what happens when x is not equal to 2 but very close to 2? So, table time. So we know that x equals 2 is not allowed, f of 2 is undefined, but what if x is a little bit bigger than 2? So if we plug in 2.1, we'll get 3 times 2.1 over 2.1 minus 2 is 0.1. That comes out to 63. Then closer to 2, so we'll have 3 times 2.01 over, the denominator is now 0.01. That comes out to 603. Closer to 2, now we have 3 times 2.001 all over 0.001. The result is 6,003. So the trend I want to see is, as x gets closer and closer to 2, the denominator gets closer and closer to 0. So when you divide by a number that's smaller and smaller, then as a result you should get a bigger and bigger answer. And that's what we're seeing here in the f of x. So let's try this time, smaller than 2, but close to 2. So we'll say 3 times 1.9 divided by 1.9 minus 2 is negative 0.1. That result, negative 57. Then we'll get closer to 2. 3 times 1.99 divided by, this time negative 0.01. The answer is negative 597. Even closer to 2. So we have 3 times 1.999 divided by negative 0.001. The answer, negative 5,997. So similar trend. As x gets closer to 2, the denominator gets closer and closer to 0, but maintains negative overall because you're coming from numbers less than 2. So our f of x values are all negative, but since I'm dividing by closer to 0, I'm going deeper into the negative. It's like a big number, but negative. So let's take a look at what this does in the context of a graph. So if x gets close to 2, if I stay bigger than 2, so I'm approaching it from the right side, my f of x values are going to become bigger and bigger positive. So what's going to occur is, as I come from the right, my y values are going to go up and up and up. Then if I come from numbers below 2, so I'm approaching from the left side, then as x gets closer to 2, my y values get more and more negative. So what's going to happen is, as I get closer and closer to 2 from this side, my y values go more and more negative. Now if I were to draw a vertical dashed line right through here, we would find that the graph gets closer and closer to this vertical line as you approach x equals 2. This behavior we call a vertical asymptote. And we say the equation x equals 2 characterizes this vertical line that we are going to approach, but we're not going to touch it. And surrounding this, we can say there is a certain behavior near the asymptote. We write this as x approaches the number 2 from the positive side, meaning from the right, f of x will go more and more positive without bound. So we say it approaches positive infinity. Then as x approaches the same number 2, but from the negative side, so we're approaching from the left, f of x is going to go more and more negative, we'll say approaches negative infinity. So what I want you to remember from this is, when you try to divide by a number very close to 0, you get a very positive or a very negative result, depending on which side you're coming from. And we write the behavior of f near the asymptote like this, and we say this is the equation of that asymptote that we're getting closer to. So now let's ask about the end behavior. So if we remember what the end behavior is, it is when x goes to very, very big positive numbers, as x approaches infinity, and x goes to very, very negative numbers, as x approaches negative infinity. So let's consider a table again. And we'll start with x is 10. So that's going to be 3 times 10 over 10 minus 2, which is 3.75. And then we'll make x bigger. 3 times 1,000 over 1,000 minus 2 is 998. And this is 3.0601. And we'll consider even bigger, 100,000. And then we have 3 times 100,000 divided by 99,998. And this comes out to approximately this. Now, the trend to notice is as x gets bigger and bigger, the minus 2 isn't very big compared to how big x is. So you notice, if you look at the ratio here of this 10 over 8, this 1,000 over 998, this 100,000 over 99,998, it's getting closer and closer to the number 1, right? As I compare x and x minus 2, when x gets very big, that minus 2 doesn't matter so much anymore. So if I hide it, I just get x over x and they cancel out, making 3. So it looks like I'm getting closer and closer to a y value of 3. As x approaches infinity, I would say f of x approaches the number 3. So I can put down a horizontal line at y equals 3 and claim that as x goes to big numbers, that's what I'm getting close toward. This behavior, a horizontal asymptote. And we write the equation for that line, y equals 3. This is the thing that we're getting closer toward as x goes to very big numbers. Now let's consider the other end behavior when x goes to very negative numbers. So we'll say, what about negative 10? So 3 times negative 10 divided by negative 10 minus 2, this is going to be 2.5. And what if I go negative 1,000? That's going to be 3 times negative 1,000 over negative 1,002. And this is going to be about 2.99401. Then negative 100,000. Here we have 3 times negative 100,000 all over negative 100,002. And that is going to come out to be something like this. So notice what's going on here. As x goes very, very negative, once again, similar logic, that negative 2 starts mattering less and less compared to how much negative that number is. So if you hide the negative 2, 3x over x, the x's cancel, and you get 3. So it looks like you're getting closer and closer to y equals 3. As x goes toward negative infinity, f of x goes toward the number 3, which is going to come out looking like that. So you might ask very meaningfully, what happens in these areas between sort of the vertical asymptote and the end behavior? And that will be a discussion for next time. But for now, the way it works, vertical asymptotes happen when you take a number and you divide it by something really close to 0. So if the denominator equals 0, you get a vertical asymptote. And the way a horizontal asymptote works is you consider the end behavior as x goes to very big numbers, as x goes to very negative numbers. And you look at the structure of the function and you judge based on every power except the biggest power doesn't matter very much compared to the biggest power. So you only look at the biggest power on the top and the bottom and look at what the function is doing. All right, let's do some examples next. Let's try example 1. So last time we started the discussion with, what is a domain? When we have a fraction, we need to make sure the bottom is not equal to 0. So let's see if we can figure out what would make the bottom 0. So we factor this and we get x plus 2, x minus 3. So that tells us that x cannot equal negative 2 because that would be 0. And x cannot equal 3 because that would be 0. So then we can write this in interval notation like this, because we're saying every number except for negative 2 and 3. Okay. The next thing we said, what happens as x gets really close to that number that it's not allowed to be? So we'll say as x approaches negative 2, and we'll start with the positive side. So in the sense of a graph, we're looking at x is getting close to -2, but from numbers a little bit bigger than -2. So I'm approaching from the right. So I would like to take a number close to -2 and put it into g of x. Now immediately I realize if I plug in close to -2, this bottom number is going to be close to 0. So I could write this as, on the bottom, close to 0, but since I'm a little bit more than -2, like -1.999, if I add 2, I become positive. So I write it like this. That means it's not exactly 0, it's a number a little bit bigger than 0. So if I divide by something close to 0, I'm expecting a very big answer. So either a very big positive number or a very negative number. And I just have to decide if the rest of this is going to be positive or negative overall. So if I take a number close to -2, multiply by 2, I get close to -4, add 1, I get close to -3. And what matters is that it's negative. Then on the bottom, close to -2 minus 3 is close to -5, so once again, a negative number. So if I say negative over overall negative, that becomes a positive number. G of x approaches a positive, but a really, really big number. That's what I'm looking at. So that behavior suggests I have a vertical asymptote, and I'm going to approach this. Then let's try as x approaches -2 from the negative side. So I'm going this way, coming from numbers less than -2. So similar deal. If I erase this and redo it, if I plug in close to -2, this becomes close to 0. But I'm a little bit less than -2, like -2.001. Plus 2 keeps me in the negatives. So I have a 0 negative, meaning close to 0, but it is a negative number. Then plug it into the rest. Close to -2 doubled is close to -4, plus 1 is close to -3, same as before. Close to -2 minus 3 is close to -5, negative as before. So negative over overall positive gets me a negative, but since I'm dividing by close to 0, I have a very negative number. I'm approaching negative infinity. That means this direction, I'm approaching that. This put together tells me I have a vertical asymptote at x equals -2. Now let's look at what happens when x gets closer to this other number it's not allowed to be. So let's say as x approaches 3 from the positive side. So there's a number 3. I'm approaching that from the positive side, a little bit bigger than 3. Think 3.001. So if I look at g of x, I say on the bottom, a little bit bigger than 3 minus 3 is a little bit positive. So I'm putting close to 0, but a positive number. And then if I put in close to 3 for everything else, double of close to 3 is close to 6, plus 1 is close to 7, a positive number. And then close to 3 plus 2 is close to 5, a positive number. What I care about is, overall this is a positive number, but since I'm dividing by close to 0, my answer is very big, positive. So g of x is going toward positive infinity. So the behavior here, once again, I have a vertical asymptote, and as I come from the right, I'm approaching positive infinity. Then, as x approaches 3 from the negative side, so I'm approaching this way, we'll erase this and look at it again. I'm approaching 3, so if I plug in close to 3, I'm close to 0. But since I'm less than 3, like 2.999, minus 3 gets me a negative number. So I'll put close to 0, but negative. And then I plug in close to 3 to the rest. I get close to 6 plus 1 is close to 7, very positive. And then close to 3 plus 2 is close to 5. Overall, this will give me a negative number, because positive over negative, which means g of x will approach negative infinity. So I have a behavior that goes down this way. These put together tell me I have a vertical asymptote at x equals 3. Okay, now let's look at end behavior. So we're going to say as x approaches infinity, meaning as x goes to really, really big numbers. So the rule is when x goes really big, the biggest power of x dominates because the smaller powers of x are just tiny compared to the biggest power. So we ignore the plus 1, we look at just the 2x on top, we ignore the minus x minus 6 and just look at the x squared on the bottom. So we would say g of x ends up looking like 2x over x squared, which we can perhaps simplify and say that ends up looking more like 2 over x. So as x goes really big, the bottom of this fraction goes really big, so you're taking 2 divided by a huge number, which gets you a result very close to 0. And then as x goes to negative infinity, so x goes to really deep negative numbers, you would say 2 divided by a really deep negative number. I mean, it's negative, but it's still very close to 0. So g of x approaches 0. So we would say as x approaches infinity that way, as x approaches negative infinity that way, the y value is getting closer and closer to 0. This is what we call a horizontal asymptote. And the horizontal asymptote has a y value of 0, so we say y equals 0. And at this stage, I can't really discuss whether I'm going to approach the asymptote from the top or from the bottom. I'm just going to go ahead and say it goes like that and it goes like that. And we'll call it good for now. That will be a later discussion. Okay, let's go example number 2. We have h of x is equal negative x squared minus 5 all over x squared plus 8x plus 16. And we want to figure out what the domain is, so we need to figure out where the bottom would end up being 0. Let's factor that denominator, and we will have x plus 4 times another x plus 4, so we'll write it like that. So we know our domain is x cannot equal negative 4, also known as negative infinity to negative 4 union negative 4 to positive infinity. And let's consider what happens as x approaches negative 4 from each side. Let's start with from the positive side. So in the graph, we have negative 4, and we're approaching it from the positive side. So we'll look at h of x, and we'll say, on the bottom, if I plug in close to negative 4, I get close to 0. But since I'm squaring it, no matter what, I'll end up with a positive number. So I'll write slightly positive. Then if I plug in close to negative 4 up here, that's close to 16, negative 16, minus 5 is negative 21, overall a negative number. So I know that h of x is going to go toward negative infinity. A negative number dividing by very close to 0 means big but negative. So I know my behavior now. I have a vertical asymptote and I'm going down this way. Okay? Then let's consider the other direction as x approaches negative 4 from the negative side, so coming from this direction. So if I redo this, if I plug in close to negative 4, I get close to 0, but since I'm squaring it, I get a positive number again. Close to 0, but positive. Take the negative 4, close to negative 4. Plug it into here. I get close to 16, negative, and then minus 5 is close to negative 21. Once again, negative number. So I will argue that h of x approaches negative infinity because I have a negative number divided by something close to 0. Thus, as I approach from the left side, I'm going to go to negative infinity down that way. This behavior tells me I have a vertical asymptote at x equals negative 4, corresponding to the fact that if I plug in negative 4, I would end up dividing by 0. That's how we get vertical asymptotes. Then, for the end behavior, we can say as x approaches positive infinity. Well, when we approach a very big number, we ignore everything except the biggest powers of x. So we're looking at negative x squared on the top and then positive x squared on the bottom. We can argue that h of x is going to basically become negative x squared over positive x squared, which these will simplify and basically become negative 1. So we would say, as x goes to very big numbers, h of x approaches the number -1. And then as x goes to very, very deep negative numbers, the same logic applies. Ignore everything except the biggest power of x on the top and the bottom. You get this same situation. So you say h of x goes toward the number -1. So we're saying that if I put down a y equals -1 line, then I'm going toward that line on both sides of that graph. So I would say I have a horizontal asymptote at y equals -1. Now see what happened in this logic. Because the numerator and denominator have the same degree, power of 2, then I'm going to look at the ratio of the coefficients on those leading terms. So -1 over +1, and that's where I got my horizontal asymptote. Let's do example number 3. We will have j of x equals, let's go x minus 3 in the numerator. We'll have 3x cubed minus 6x squared minus 24x in the denominator. Same discussion. We want to know the domain. So let's factor the denominator and see what happens. So it looks like we can pull a 3x out of all of that. So I can write this as 3x times x squared minus 2x minus 8. And then that factors down into x minus 4 times x plus 2. So I can write down 3x times x minus 4 times x plus 2. And now that I have all of that, I can erase this and we're good to go. My domain, x cannot equal any of the numbers that would make the bottom 0. So that would be -2, 0, and 4 in that order, which means in interval notation, I would have a domain looking like this. And I'm suspecting that I should get vertical asymptotes at x equals 0, x equals -2, and x equals 4 because I'm dividing by 0 at those locations. But just to check, let's consider the behavior near those values. So I'll start by doing that. So in the graph, this is what we look like. So the concerning values for us are -2, 0, and +4. And I'm going to approach the -2 from the right side. Okay, so we'll write down j of x equals, and in the numerator, if I plug in close to -2, that's going to be close to -5, overall negative. Then close to -2 times 3 is close to -6. Then close to -2 minus 4 is close to -6. Finally, if I plug in close to -2, this turns out to be close to 0. So I say I'm a little bit bigger than -2, like -1.999. Plus 2 gives me a little bit positive. So I'll put down 0 plus to indicate close to 0 but positive. Now overall, negative divided by positive gives me negative. And since I'm dividing by close to 0, I'm going to get, that is a j, approaches -infinity. So the behavior, I now know I have a vertical asymptote. I'm going to go down toward -infinity. Okay. Let's try as x approaches -2 from the negative side. So I'm coming from the left. So now here, what's going to change is just this, but nothing else. Because I'm still letting x be close to -2, so that would be still close to -5, still close to -6, still close to -6. None of that changes just because I'm a little bit more than or less than -2. What changes is this part, which is close to 0. So this time my x is a little bit less than -2, so like -2.001, plus 2, I'm still negative. So I'm close to 0, but negative. Now, on the top negative, on the bottom negative, overall that division gets me, j of x goes to a huge positive number. So I can say, I approach positive infinity. Vertical asymptote, x equals -2. Now, let's do this with the next place we're not allowed to be. So we'll say, as x approaches 0 from the positive side. That means we're approaching this from the right. So when I plug something close to 0 in, close to 0 minus 3 is close to negative 3. This time, this is the interesting one. So I'm close to 0, which means this is close to 0, but I'm a little bit more than 0, so this is a little bit positive. Close to 0, but positive. Then close to 0, minus 4 is a negative number. Close to 0, plus 2 is a positive number. So negative divided by negative is going to give me a positive result, but since I'm dividing by close to 0, I go positive big. So what I will have is this behavior. Then, as x approaches 0 from the negative side, so I'm approaching this way, I'm a little bit less than 0 now. So none of these things change because I'm still close to 0. Those are all close to whatever numbers I said they were. What changes is this, because I'm close to 0, but last time I was bigger, now I'm less than. So this time I'm a little bit less than 0, close to 0, but negative. Now overall, on the top negative, on the bottom positive, I'm going to get a negative result. So j of x is going to go toward negative infinity. That tells me this behavior. And I should put a vertical asymptote right through here. So I know I have a second vertical asymptote at x equals 0. We can erase this and do the analysis again for close to 4. So I'll say, as x approaches 4 from the positive side, coming this direction. So close to 4 minus 3 is close to 1, that's positive. Then close to 4 times 3 is close to 12, is positive. Close to 4 minus 4 is close to 0, but I'm a little bit bigger than 4. Subtracting 4 leaves me a little bit bigger than 0. Then close to 4 plus 2 is close to positive 6. Overall positive tells me j of x goes toward positive infinity. So I'm going to slap down a vertical asymptote right here and go up toward positive infinity. Now, as x approaches 4 from the negative side, so the analysis now, I'm a little bit less than 4. Those are still going to be the same, but now I'm a little bit less than 4. Subtracting 4 gets me a little bit less than 0. That's a negative number now. So overall positive on top, overall negative on the bottom. My result should become a negative number. Dividing by close to 0 pushes me toward deep negatives. So I will have deep negatives down here. So that's the behavior around all of my vertical asymptotes. Then finally, we'll check the end behavior. So we'll say, as x goes toward positive infinity. Well, if we make x a very big number, the top only the x matters, and on the bottom only the 3x cubed matters. So we would say j of x is going to go toward something that looks like x over 3x cubed, which will simplify to something that looks kind of like 1 over 3x squared. Then when x goes to a really big number, 1 divided by a really big number gets closer and closer to 0. So my y value approaches 0. Then as x approaches negative infinity, same logic, only look at the biggest power on the top, only look at the biggest power on the bottom. That reduces to something that looks like that. If I plug in a very negative number, I still get something huge on the bottom, so my y value approaches 0. So I would argue that there is a line y equals 0 through here, and I'm going to approach that some way toward the right and toward the left. I would argue then I have a horizontal asymptote at y equals 0. Let's do a quick recap. We have a rational function f of x, which has a polynomial numerator and a polynomial denominator, and I can write the numerator in our standard notation for polynomials, all the way down to a sub 1x plus a sub 0. And on the bottom, I can write that in the same way using different letters to indicate that they don't need to be the same polynomial. And the deal is, we discovered that there's a certain behavior called a vertical asymptote when the denominator is equal to 0. And strictly speaking, the numerator has to not be 0, and we'll talk about why that is next time. So, if the denominator is equal to 0, you get a behavior that's sort of like this, where on one side you might go to positive infinity, on the other side you might go to positive or negative infinity. Interesting things can happen, but you are not allowed to be that number for x. Then there was the horizontal asymptote, which is based on the end behavior. It's as x goes to infinity and as x goes to negative infinity. And there are 3 cases that result out of this. We look at the degree of the numerator and the degree of the denominator, so n and m. So it turns out if n is less than m, so the top is a smaller degree than the bottom, then when you plug in a big number, the bottom is so much bigger than the top that you get the horizontal asymptote is y equals 0. Now, if n is equal to m, so you have the same degree on the top and the bottom, we showed that it simplifies down and you just look at the ratio of the leading coefficients. You end up with a horizontal asymptote at y equals the ratio of those leading coefficients. And the one case we didn't see today, but we'll see later, is if n is bigger than m. So the top degree is bigger than the bottom, then you have no horizontal asymptote. You will get other interesting behaviors. All right, thanks for tuning in. Good luck.